Hello everyone, welcome to all. So in this PDC lecture series, we will try to solve one numerical for the tuning of proportional controller in the feedback system. So in this problem, we have given that for each control system shown in figure, determine the characteristic equation of the closed loop response and determine the value of Kc that will cause the system to be on the verge of instability. Find the ultimate gain Ku. If possible, use the Routh test. Note that feedback element for the system B is an approximation to e to the power minus 2s. So here we have given two negative feedback system for the same process. In the first system A, we have a measuring element which has the transfer function e to the power minus 2s, and in the system B we have an approximation to this transfer function which is represented by an exponential function. Therefore, we have to find out the value of Kc for the two different control loops. So let's begin, and here we will use frequency response analysis for the system A, as it contains the exponential term in the feedback loop. For the system B, we will use Routh array test to find out the state at which the loop will be on the verge of instability, or the system will be marginally stable. So let's begin with system A. So using the conventional block diagram for negative feedback system, so let's draw a conventional block diagram as follows. So here we have comparator, here we have set point R, then we have controller GC, then we have the final element GF, then we have another summing point where another load U is coming, and next we have the process GP, and then we will get the final output C. Now this C is measured by an measuring element H, and which will give a response variable, and it will compared with the set value, and this way we will get the negative feedback loop system for any process. So if we compare this conventional block diagram with system A, so for system A, we have set point KC, GF, let's say 1, GP is something, a combination of two first order system, and it can be written as, let's say, 1 upon 8s plus 1 1 upon 8s plus 1 and here we will get the control variable C. Now we have another measuring element with the transfer function e to the power minus 2s, and this is the response of this measuring element is compared with the set value R. So the system A can be written in this way, right? So here this is G1 and G2, this is H, this is GF, this is GC. So finally we have different types of elements in the series. So to find out Kc, we will use Ziegler-Nichols method. Applying Ziegler-Nichols tuning method for system A. So in Ziegler-Nichols method, we know that we have two parameters, which need to be find Ku, the ultimate gain, and Pu, the ultimate period of oscillation. So to find out these two parameters, we have to find out the crossover frequency, and to find out the crossover frequency we need the expression for phase shift, and to find out Ku we need the gain margin. So here Ku is the ultimate gain and which is gain margin and that is 1 upon m, and m is the amplitude ratio of the system at the crossover frequency. Similarly, the ultimate period, the ultimate period Pu is given by 2 pi upon omega co. So where omega co is the crossover frequency. So now let's find out the crossover frequency. So to find out crossover frequency, we need the expression for phase shift, which is the function of omega. So as we know that the phase shift is given by the argument of j omega, and g is the transfer function for the required open loop. So here in the Ziegler-Nichols settings, we generally omit the controller action by removing the GC terms from the open loop systems. So, and we introduce the controller action with only the proportional controller for the loop which contains the final element GF, the process GP, and the measuring element H. So here we will find out the open loop transfer function, which includes only 3 elements GF, G1 or G2 or H. So G1, G2 are the approximation for the GP. So we will only consider the transfer function for the final element GF, the transfer function for process GP, and the transfer function for H while considering the open loop transfer GOL. Or we can say we can consider GC is equal to 1. So as we know that the open loop transfer function, GOL is given as GC, GF, GP or H. So in the case of Ziegler-Nichols tuning, so this GC will be equal to 1. So finally the open loop transfer function will become GF, GP or H. So we will consider only these three elements while using the frequency response analysis. So and therefore GOL of S can be written as GF S G1 of S G2 of S H of S, and here this is nothing but GP of S. So GOL of J omega will be equal to GF of J omega G1 of J omega G2 of J omega and H of J omega. So therefore the amplitude ratio will be equal to the modulus of open loop GOL of J omega, and which will be equal to GF of J omega G1 of J omega G2 of J omega and H of J omega. So therefore if you see here, AR will be equal to, since GF is equal to 1, so AR will be equal to mod of 1 mod of 1 upon 8 S plus 1. So 8 S so in this, so this will be 1 upon J 8 omega plus 1 upon J 8 omega plus 1 and e to the power minus 2 omega j. So the amplitude ratio will be equal to one upon under root 1 plus 8 omega square into 1 upon under root 1 plus 8 omega whole square into 1. So amplitude ratio will be equal to 1 upon 1 plus 8 square omega square, and that will be equal to 64 omega square. So this is the expression for amplitude ratio. Now we will find out the phase shift. So the phase shift phi can be written as the argument of open loop transfer function GOL j omega, and that will be equal to the argument of GF plus the argument of G1 plus the argument of G2 plus the argument of H. So finally phi will be equal to, so the argument of GF, so the final element, so the final element is 1, we have assumed. So the argument of 1 plus the argument of 1 upon 8 omega plus 1 plus the argument of 1 upon j 8 omega plus 1 plus the argument of e to the power minus j 2 omega. So the phi can be written as, so this will be 0 plus tan inverse minus 8 omega plus tan inverse minus 8 omega plus minus 2 omega. So the phi will be equal to 2 tan inverse minus 8 omega minus 2 omega. So this is the expression number 2 for the phase shift. So this way we have found the expression for amplitude ratio as well as the phase shift. So the next step is to find out the crossover frequency. So to find out crossover frequency, we have to use phi equal to 2 tan inverse minus 8 omega minus 2 omega. So using this expression, we know when omega equal to crossover frequency omega CO, the phase shift is minus 180 degree or minus pi radian. So therefore we will use 2 tan inverse minus 8 omega CO minus 2 omega CO plus pi equal to 0, and finally we will solve this non-linear expression to find out the crossover frequency. So by trial and error, we will find omega CO. So let's say omega CO is pi, and we will find out this value. So this function value, let's say this left hand side will be equal to some number, right? Next we will use crossover frequency equal to some another number. So generally this pi is 3.14, omega CO is equal to 2, and we will find out the left hand side. Use the calculator. So here we will use the calculator. So before using the calculator, first make sure the angle unit is radian and it is selected. Okay. So the next step, we will use this expression number 3, 2 tan inverse. So we will use 2 into shift tan inverse minus minus 8 omega CO. So 8 so the value of pi is 3.14. So bracket close minus bracket open 2 into 3.14 bracket close plus pi. So here we can see we are getting minus 6.2. So when omega CO is equal to pi or 3.14, the left hand side is minus 6.2. So this is minus 6.2. So now let's change omega CO is equal to 2. So now let's change this with 2. So now we are getting 3.8. So minus 3.8. But again this is negative, this is negative. So now let's use omega CO is equal to 1 radian, and let's put so minus 1.7. So omega CO 0.5. So if we put omega is equal to 0.5 0.5, we are getting minus 0.5. So left hand side equal to minus 0.5. So it's decreasing, but the sign is still negative. So 2 tan inverse minus 8 omega minus 2 omega plus pi. So that's our expression. So let's use omega CO is equal to 0.1. So the left hand side will be equal to, so if we put this is omega CO equal to 0.1, so we will be getting 1.5. So left hand side is become 1.5, which is plus, and when omega CO is equal to 0.5, we are getting negative. So when omega CO is equal to 0.5, we are getting negative. When omega is equal to 0.1, we are getting positive. So the roots will lie in between these two numbers. So let's omega CO is equal to 0.5 plus 0.1 by 2, and that is 0.3. So left hand side will be equal to, so now again calculate left hand side using omega CO is equal to 0.3 radian. So now we are getting 0.189. So now we are getting 0.189, but the sign is still positive. So the root will lie between this 0.3 and 0.5. So here the crossover frequency will be 0.3 and 0.5 half. So let's say this is 0.4. So at 0.4, let's find out the function value. So here instead of just replace 0.3 with 0.4, so we are getting minus 0.19. So minus 0.19. So here we are getting minus 0.19, and at 0.3 we are getting positive. So the root will lie in between. So let's use omega CO is equal to 0.35 radian and find out the function value at this point. So replace this with 0.35, and we will get minus 0.01. So minus 0.01. So which is still negative. So the root will lie between. So the root will lie between this 0.35 and 0.3. So using trial and error, so now let's assume omega CO is equal to 0.32 and 0.32. So again we are getting positive. At 0.3 we are at positive. So now let's use this as 0.3 when omega CO is equal to 0.33. So the left hand side equal to, the function value is equal to 0.06. So 0.06. So the root will lie between these two numbers, 0.33 and 0.35. So if you see here, if we replace 0.33 with 0.34, we will be getting 0.02, but it's still positive, right? And this will be 345. So when omega CO equal to 0.345, the left hand side or the function value becomes 0.005, so which is nearly equal to 0. So the crossover frequency will be equal to 0.345. So we can take this as approximation. So once we know this crossover frequency, we can find out the ultimate gain as well as ultimate period. So the ultimate period can be calculated as 2 pi upon omega CO, and this will be equal to 2 pi upon 0.345 radian. So 2 pi upon 0.345. So this will be equal to 18.21. So this will be equal to 18.21. Similarly, we can find out the ultimate gain, which will be equal to 1 upon m, and m is the amplitude ratio at omega CO. So first calculate m. So m can be calculated from the expression 1, and expression 1 equal to AR equal to 1 upon 1 plus 64 omega square. So m will be equal to 1 upon 1 plus 64 omega CO square. So that is equal to 1 plus 64 into 0.345 whole square, and that will be equal to, so 1 upon 1 plus 64 into 0.345 square. So this is 0.116. So this is 0.116. So if we put 0.116 in the expression of ultimate gain, we will get, so 1 upon 0.116. So this is 8.62. So this is 8.62. So this is 8.62. So for P controller, so using Zn table, so using Zn table, we have P controller, PI controller and PID controller. We have Kc, tau I, tau D. So this P controller Kc equal to Ku by 2. For PI controller, this is 0.45 times Ku. For PID controller, this is 0.6 times Ku. For PI controller, tau I equal to Pu by 1.2. For PID controller, tau I equal to Pu by 2, and for PID controller, tau D equal to Pu by 8. So we have Ku value equal to 8.62 and Pu value equal to 18.21. So 18.21. So using this value we can find out. So 8.62. So this will be 8.62 divided by 2. So this will be 4.31. So this will be 4.31. For PI controller, 8.62 into 0.45, 3.879. So this will be 3.879. For PID controller, 8.62 into 0.6. So this will be 5.2. So this will be 5.2. Similarly, for PI controller, tau I will be 18.21 divided by 1.2. So 18.21 divided by 2. So this will be 9.1. So this will be 9.1. And next, 18.21 divided by 8, we will be having 2.28. So this will be 2.28. So for the system A, we have found different types of parameter Kc, tau I and tau D for 3 different controller P, PI, PID. So now for system B. So for system B, we have R, we have Kc, and we have 1 upon 8s plus 1 whole square C and one minus s upon 1 plus s. So this is the approximation for the system A as given in the problem. So if you see here in this problem, so for system B we have Kc, the process is 1 upon 8s plus 1 whole square, and the h is 1 minus s upon 1 plus h. So using this we will find out the open loop transfer function. So the open loop transfer function will be GC, GF, GP and H, and this will be equal to KC. GF is 1, so this will be 1 minus S upon 1 plus S, 8S plus 1 whole square. So next we will find out the characteristics equation. Characteristics equation which is given by 1 plus open loop transfer function equal to 0. So one plus Kc 1 minus S upon 1 plus S, 8S plus 1 whole square will be equal to 0. So finally we will get 1 plus S, and here 64S square plus 8 to the 16 S plus 1 plus Kc 1 minus S equal to 0. So further simplifying we will get 64 S square plus, so 16 or 64, so 80 S square, then we have 16S or 1S, 17S, so 17 minus Kc S plus Kc equal to 0. So this is the characteristic equation which is given by equation number 4. So here we will use Routh stability criteria. So using Routh stability criteria, so here we will make the Routh array. So the first column is row, and then we have column number 1, and then we will have column number 2. Since the maximum degree of the polynomial is 3, we have a cubic polynomial, so we will have n plus 1, that is 3 plus 1, 4 row. So first 2 row will be given as follows. So this will be 64, this will be 80, this will be 17 minus Kc, and this will be Kc. So the next row number 3 and 4 can be calculated as follows: B1, B2, C1, and C2. So where B1 equal to upon 80, and here we will have 80 17 minus Kc minus 64 into Kc. So this will be equal to 80 into 17 minus 144 Kc upon 80. So B2 will be equal to, upon 80. So we will just, so to calculate B2 we will hide the column C2. So in the denominator we will have 80 and then 80 into, so this is C3, so 0 and 0. So we will use this 80 into 0 minus 64 into 0. So finally B2 will be 0. So C1 will be equal to upon B1, and this will be B1 into Kc minus 80 times B2, and B2 is 0. So we will have so C1 will be equal to Kc. Similarly C2 will be equal to B1 and this will be B1 0. So B1 0 minus 80 0. This will be 0. So this way so finally in the first column we have the element. So in the first column C1 we have 64 comma 80 comma B1 comma C1, or 64 80 and we have 80 into 70, 80 into 17 minus 144 times Kc upon 80 and Kc. So in the first column we have these elements, and for stability So for stable system, all the elements in column 1 must be positive. It means this B1 should be greater than 0 or 80 into 17 minus 144 kc should be positive, or we can say this kc must be less than 18 into 17 by 144. So if you see here, 80 into 17 divided by 144, this should be 9.44. so kc should be less than 9.44. So for the stability, the system gain should be less than 9.44. Similarly, at the verge of instability, this B1 should be equal to 0. It means kc it means 80 into 17 minus 144 kc equal to 0, or kc should be equal to 80 into 17 by 144. It means kc must be equal to 9.44. So when kc equal to 9.44, the system is marginally stable. So here we can see from the Routh stability, the ultimate gain equal to 9.44, and from the frequency response analysis using Ziegler-Nichols, the kc equal to 4.31. So this numerical shows how one can approximate the different types of complex transfer function, like transportation lag, and find out the ultimate gain using Routh stability. So thank you